Hi, so we're in part two of our lecture number 4, and we'll be continuing with this idea of a function. So in this last part, we've talked about the equivalent terms for inputs, which are x values, independent variable, and this term domain, which we're going to be considering a lot more now. And we have the equivalent terms for outputs, which are y values, dependent variables, and the range. So these are the ones that are paired. So I can maybe make a pairing. So domain and range are usually utilized in tandem. The dependent variable, independent variable are another pair. And of course, the x and y values are a pair. Okay, and so now we're gonna be discussing what's called the function notation. So there's a way that we describe functions, and it's usually given by this kind of format. Either we write it as y equals f of x or f of x equals y. So I'll write this, or y equals f of x. So that's the function notation. These parentheses are not multiplication. So we're not gonna, you know how we normally have like 3x plus 2 and there's a 5 in front, and then we distribute because there's this multiplicative property associated with that. These parentheses are not that kind. We're not going to be distributing. We're not going to be distributing the f into the x. That doesn't make sense in this case. In this scenario, f represents what's called the name of the function. This x here represents the input of function. And then this represents the output. Okay, so we have the input, we have the name of the function, and we have the output of the function. Remember what we talked about. X, we talked about it right here. X values represent the input. The Y value represents the output. So we can also bring back the idea of the machine diagram. This is why the machine diagram is utilized. Because you can think of this as saying, hey, I'm going to plug in the X value into this machine called F. And now F can be described in many ways. So let's see if we can show an example of that. So an example of a function, I'm going to define a function. I'm going to say f of x is the function that does the following. It takes x, then cubes it, or raises it to the third power, multiplies it by 5, then you subtract 6 times x minus 2. So what we're going to be slightly touching upon is something called evaluating a function. So what do we do with functions? We evaluate it. Evaluate a function. Now, what does that mean? This just means find the numerical value of, or I can also say find the numerical or algebraic sorry, I spelled algebraic wrong, algebraic value of the output given a specific input. So for example, if I say evaluate f, and then parentheses -3, I want to find what the y value is. Remember, input is the x value, and the output is the y value. So when we say evaluate a function is I'm given a specific x value. This is my specific x value, and I'm trying to figure out what is the y value. That's all it is. And one thing I want to say is that when we say this, when we say this term in words, f parentheses x, we say the following. We say f of x. So this is how it's um, read in words. Read in words as f of x. So we say f of x. So we're saying f of x is equal to 5x cubed minus 6x minus 2. Now, what does that make me do? That tells me, hey, take f of negative 3, and every single place I see x, I'm going to replace it with negative 3. So this is going to be a 5, negative 3 cubed minus 6 times negative 3 minus 2. So all I did was I replaced. So replace the x variable with the specified input value. So my input value is negative 3. So every single place I see x, I plug in negative 3. And then I just apply the PEMDAS operations. So then I get what? I get 5 times negative 27. Then I get negative 6 times negative 3 is positive 18 minus 2. Then 5 times negative 27 is negative 135 plus 16. And if you equal this becomes negative 119. So what did I just figure out? I figured out that the value of the function, so I'm going to say this in words. So this means, this result means that the value of the function f of x at x equals negative 3 is negative 119. That's how you would say this in words. You would say the value of the function at negative 3 is negative 119. In other words, the x value is associated to the y value of negative 119 in this particular example. So hopefully you start to see now how all these different facets of the function can actually be understood now. Not only are we just numerically finding the x and the y value, now we can, if we want, we can create a coordinate, an ordered pair, x comma y. Well, that's exactly what we're doing. We're taking the x value and finding the y value. So another thing we can say, this results means that, and the first thing we can say is that the value of the function is f of x at x equals negative 3 is negative 119. The second thing we can say is that the y coordinate, the coordinate is of the function is the following. So not the, but a coordinate, a set of coordinate, a coordinate for the specified, for the function is negative 3 comma negative 119. So what does that mean? That means that I can plot this point on the graph at negative 3 go to negative 19 and plot that point, and that point is on the graph of f of x. So that's how we can find the different values of f(x). We just plug in different values for x, and then we get correspondingly different values for y, make them into pairs, into ordered pairs, and then plot them on the graph, and boom, you can connect the dots afterwards, and then you have the graph of the function. So that's what evaluate means. It just means plug in the x value and find the y value. That's what evaluate the function means. So we can say plug in x value to find y value. That's another way you can think of evaluating a function. And now, without getting too crazy with this, we can also plug in things that are not necessarily numbers. Um, like for example, let's say my function is 2x plus 5, right? And then I want to evaluate the function. This time I'm going to plug in a different expression, h plus 3. Now this may seem a little strange. You're like, but why are we doing this? This is not a number anymore. This is an algebraic expression. But if you think about this, you can really think about this as the following. This is like saying f of the input equals twice the input plus 5. That's really the more general perspective of what a function is. Plug in the input, and now what is my function being defined as? It's being defined as twice the input, whatever it is, plus 5. In this case, the input is h plus 5. So now look what I can do. I can do 2 multiplied by h plus 3 plus 5. Then what can I do? Then I can distribute the 2, and I get 2h plus 6 plus 5. And the result is 2h plus 11. So this is where it gets a bit more on the algebraic perspective, because we're plugging in an algebraic expression for x, and my y value is also another algebraic expression. So again, this is my input, and the result of that is my output. I just evaluated a function. The only difference is, in this particular example, it's an algebraic expression, which has letters in it. And the previous example, we only had numbers in it. But the process, the idea is exactly identical. So that's evaluating a function. We talked about domain and range, and we talked about how a function can be expressed as a set of ordered pairs. So finding the domain and range of a function. So that's one thing we're going to be definitely be interested in. How do you find the domain and range of a function? So I'm going to call this like scenario 1. The first scenario is when you have a set of ordered pairs, when function is expressed as a set of ordered pairs. So I'll give you an example of that. What happens if I have the set 3 comma, pardon me, 5 comma 3, 9 comma 7, 13 comma 7, 17 comma 3. Okay, so we have, remember, we can express a function into a set of ordered pairs, x comma y coordinates. Now, what we're going to do is I want to find, first of all, is it a function? Well, if we look at the x values, they only appear once, right? So since x values only repeat once, then this is a function. This represents, and this set represents a function. Okay. And since it represents a function, we care about what's called the domain, and we care about the range. Now, what's my domain? My domain is the set of all x values. My range is the set of all y values. We talked about this, right? So what are all the x, what is the set of the domain? It's just a set of all x values. So we want all the x values. all x values. And the range will represent all y values. So all the x values are what? 5, 9, 5, then comma, 9, then comma, 13, then comma, 17. Remember we talked about the set using the curly braces, and then the range are what? All the y values. And remember, the y values can repeat, so that's okay. So the y values here are 3, 7, 7 repeats, and 3 repeats. So I only have to write 3 and 7 once. And that's what I was able to figure out. I was able to figure out the domain, find all the x values, and the range, all the y values. That's it. That's how you find the domain when you have a set of ordered pairs. Now, what if I don't have a set of ordered pairs? What if in the second scenario, my function is expressed in a graph? My function is visualized as a graph on the Cartesian plane. Now, what if I have a function like this? What if I'm given a graph and I have to figure out my domain and range? So what if I have something like this? So these lines go on forever. This point right here, I'm gonna call this 5, and this is 2. Now, this line here goes on forever to infinity and beyond, and so does this line go on forever upward to infinity and beyond. Now, I care about my domain again. So we're going to be caring about the domain and range of the function. Now, for this kind of scenario, remember, in this scenario, we only look at the x values and the y values, and we're able to pick them out very easily. In this scenario, we have to think about this a little bit differently. So what would be the domain? The domain, remember, doesn't change, are all the x values. But now, these x values, what are the x values for this function? Well, if you notice, for every x value that you choose, there's always going to be a y value. It doesn't matter how far away you are on the x-axis, whether it be to the right or to the left, doesn't matter where I am. I'm always going to have a particular x value, right? Since this goes on forever. So because that's the case, the domain here is negative infinity to infinity, also known as, this also means all real numbers. All real numbers. Because we're saying for any x value, this works. In other words, for any x value, I can plug into this function, get a y value associated with it for any x value. It doesn't matter what it is. So therefore, my domain is negative infinity to infinity. Now the question is, what's my range? My range are all the y values. Now, if you notice, the y values, we have to now look at this axis. We don't care about this axis now because we're looking at the range. Now, if you look at the y-axis, you notice that this also goes up to infinity, right? So then my y values go all the way to infinity. But then if there's a certain point where my y values never get below a certain value. And that value, since this has like a minimum y value, this value is like a cap for the range. So the range includes everything above 2, including 2, but nothing below 2. So the range using the interval notation. So I'm going to be expressing domain and range in this case in interval notation. So it would be 2 comma infinity. So we're utilizing what we've discussed about how to express sets in interval notation. Now we're bringing that onto on this side of mathematics, which is finding the domain and range of a function. So I hope that makes sense in terms of visualizing what the domain and range is and utilizing interval notation. So for this kind of problem, we use interval notation for the most part to express domain and range for graphs of functions. Most of the time, our graphs will be some kind of connected curve, line. So our domain and range will be some kind of interval. It's not going to be the way we found the domain here, which are just specific points. So that's why we wrote the set as specific numbers. In this case, our domain is now an interval notation because of the way the function is described. Okay, and this can get kind of fun if you look at it. Like for example, if I give you something like this. So I'm choosing this point right here. This is my function, and it's a graph. And I want to find out what's the domain and range. So what's the domain here and what's my range? So remember, the domain are all the x values. What are all the x values? Well, they're the points where they're associated with the x value, there's a certain y value. So you see all the points that are above -4, including -4, because right here is a solid circle here. At this point here, what's my coordinate? My coordinates are -4, 0. So at this point here, I have an x value, which is -4, and a y value, which is 0. However, anything below -4, I have no y value. There's no associated graph to it. So my domain is going to be from -4 to 0. Okay. And then the range, what's the range going to be? The range is going to be everything above 0. If you look at the y values, right? If you look at the y values, it's going to be everything from 0 and above. This will be 0 to infinity. Do you see that? So that's going to be the domain and range for this particular graph. Okay. So that's how we're going to be looking at graphs and determining the domain. We're going to be looking about how the x values are, how we can figure out what's the interval for the x values. So we look at the x-axis for that. And what are the y values associated with? And we look at the y-axis for that. So hopefully you see that there's nothing below the y value for this. Before, there's nothing below the 0 value for y. There's nothing here that is associated with the y with the curve. So because of that, every point here has a y value that's bigger than or equal to 0. So therefore, the range is from 0 to infinity. Okay, so that's how you find the domain and range of a function if you have set ordered pairs, or if you have a graph of a certain function. Okay, now I'm going to say let's ways to determine whether a graph is a function. Whether a graph is a function or not. So this is something that's called we use we use the vertical line test. And how do we use this vertical line test? Let's give you an example. So if we have a function like this, just like a regular curve, and if you notice, so what we're going to do is we're going to draw vertical lines. Draw vertical lines. So when I do that, let's make these straight lines. Draw vertical straight lines. So if I draw straight lines, any vertical straight line that I get, I only have one point of intersection. So I drew vertical lines, and my observation is every vertical line crosses the graph once. Hence, the x values are repeated only once. So then what's the conclusion? By the vertical line test, the graph is a function, or the graph represents a function. So do you see how the vertical line test determines whether or not the graph is a function? Because the vertical lines are crossing the x of the curve, these vertical lines indicate that only one x value at each of those points is associated with this graph. Because every point that we get, every line that we draw only intersects at one time, that means that there's, for every x value, is only one y value. And because of that, we can say with certainty that this function does represent, this graph does represent a function. Now, what if I have an example of a graph that looks something like this? A circle, just a good old circle. What happens the moment I just draw one vertical line? In that moment, I know exactly that it crosses it twice. So then we say, again, we use vertical line test, right? So use vertical line test. The first thing we observe is that one vertical line crosses a graph twice. So if that's the case, that means that there's an x value somewhere here that has two y values. So then we say, hence, there is a repeated x value. But remember what we said, we can't have repeated x values. So then the conclusion is, by the vertical line test, the graph does not represent a function. And that's it. And so then that represents, this is how we utilize the vertical line test. Very simply, just draw vertical lines, draw lines that are parallel to the y-axis. So if you draw those lines, and the moment you draw one, you only need one vertical line that crosses the graph twice, that indicates the x value has associated two y values associated with that one x value. And because that's the case, then that graph cannot be a function because that contradicts the definition of the function. And so we are done with this portion of the lecture.